Hi there. So in this session, we're going um, to talk about the application of Newton's law, second law of motion. Okay, for those objects, for those system wherein the acceleration is not equal to zero, so we are going to have that. Okay. So what's this? So let me remove this one first. Okay, so second law. So whenever the system is accelerating, then it is not anymore in the paradigm of statics. Rather, it is already in what we call as dynamics. Okay, so you have here the paradigm of dynamics. Okay, so dynamics, this involves systems which are accelerating. So we're going to have sample problems in this matter. Okay, so we are going to have this first problem. So we're going to start with the easier one, then to a more complicated problems. Okay, so I'm going to zoom this one in. Okay, so you have your sample problem number 1. An object with a mass of 10 kg, of course, is placed on the horizontal floor, and of course it is being pulled by a rope. So when we talk about rope, of course, the force involved in here is tensional force, and in this problem we are trying to neglect the mass of the rope so that we are not going to complicate the system. Okay, so the rope is pulled at a certain angle, that is 30-degree angle. That is a 30-degree angle, and we have here the frictional force acting on the system, acting on the block or the object. So you have here. So what will be the acceleration of the object? That's what we're going to find. Okay, so we have here the figure of the system. Okay, so you have here the photo. So you have here the frictional force, which is 0.04. This is what we call as the coefficient of static friction. I mean kinetic friction, because the system is moving, or the block or the object is moving. Okay, so the next thing that you're going to do after making a picture of the scenario or the problem is that you're going to superimpose the forces on the Cartesian coordinate system. Okay, so you have here the forces. So just imagine that the center of the box, it is where every forces is acting on. Okay, so you have here the normal force going upward. This is the force exerted by the floor, supporting, of course, the object. And you have here the weight of the object, that is mass times gravitational acceleration. Then the acceleration of the force, of course, would have to be in this direction. So the acceleration of the force will be in this direction. Okay, so since the acceleration is going to this direction, then automatically the frictional force will be an opposite to the acceleration, because friction is always opposite to the motion of the object. Okay, so you have there. So the next thing that we are going to do is actually to decompose the system. Okay, so you have there decomposition. I mean, not the system, but the tensional force. You have to decompose this one. So you have here this force, that one. Then you have, this is your T sub X. Then we have another force, this one. We have P sub Y. Okay. Then the next thing that you're going to do, of course, is to define what is t sub y and what is t sub x. So basically, using a trigonometry, this side here is opposite to the angle, so this is t sine 30, while this one is t cosine 30. Okay, then apply the laws of motion. We're going to apply the laws, the second law, along x-axis and of course along y-axis. Okay, so you have here the force along y, then you have the force along x. So in this system, we all know that the object is not moving vertically, rather it is moving horizontally. Okay, so you have here the direction of the acceleration going to this direction. So this is the direction. So along y, no acceleration. Okay, so along y, so there is no motion. Okay, so you have there. So we're gonna use the equations now. So these equations emanated from what's happening. Okay. So the equation actually emanated from the figure that is being created, or the free body diagram. So the first thing being attacked is actually the y. So since along y acceleration is equal to 0 along y, so you are going to have the summation of forces along y is equal to 0. So what are the forces along y? If you're going to go back to the figure, so we have here the normal force. You have there the normal force. You have this t sub y, that is t sine 30, and of course the gravitational acceleration. So you have there. Then you plug that one in. Along x, so we have only the frictional force and of course the t sub x. Okay. So you have there. Along y, you have the normal force going upward. That is why it is positive. Then the t sine 30 that is going upward also, that is positive. Then you have the weight, which is m times g, going downward. That is why you have the negative, and then equate that one to 0. Then we now have the normal force, because you know normal force is very important in computing for the magnitude or the value of your frictional force. Okay, so you have the normal force that is equal to mg minus t sine 30, and of course the normal force is equivalent to 733 Newton. Okay, so you have there. You might be asking, where did I get this 1/2? Well, sine 30 is 1/2. You may recall, you have here this 30, you have 60, 90. So this is special. So this part here is of course 1/2. This part here is square root of 3 over 2. Then you have here 1. Okay. So that's it. Remember that sine 30 is 1/2. If in case you have no calculators, you may and then the given is actually a special triangle, then you may opt to use this technique. Okay, so we are the forces along y is now being summed up, and we come up with the normal force to be 73 Newton. Then next thing is we're going to have along the x-axis. So along x-axis we have here this the acceleration, which is assumed to be going to be in a positive x direction. So you have here the summation of fx is equal to ma, because again the system is in dynamics. So acceleration along x is not equal to 0. Okay, so that's why we were able to apply this second law of Newton. And then what are the forces along x? So we have here that t cosine 30. This is a component of the tensional force going to x direction. Then you have here minus f, because that is opposite the direction, then equals ma. So by definition, we have here F is equal to mu times N. So in this case, you have kinetic friction. Then we're going to use that one in here. So that is why you have here mu times N is equal to ma. Then further, you rearrange the equation. Okay, so divide both sides by m. So then plug in all the values. We have 50 times 0.866. This is equivalent square root of 3 over 2, if I'm not mistaken, minus, you have the coefficient friction 0.04 times 73 Newton. Okay, so you have there, this 73 Newton refers to the normal force. Then the acceleration of the system is equivalent to 4.038 meters per second squared. This is taken to be positive because it is going to positive x-axis. Okay, in other problems that we are going to have, okay, there are different interpretations. Okay, particularly the inclined planes, those problems. Okay, then basically we have here this another problem. It's the difference of this problem is actually you have here two masses or objects. Okay, so the two objects, they have their respective masses, and we baptize these objects. The first one is from the left. They have MB, and the second one is MA. That is going to the right. Okay, and it's being pulled, connected by a cord, and the cord is negligible mass again, so that it will not contribute to the system. Then it is being pulled by a force, which is equivalent to 40 Newton. So you have also there the coefficient of friction, meaning to say that the system is non-frictionless system. So what is asked here is actually the what we call as the acceleration of the system. Okay, so in this problem, basically we have to create two systems. We have here for system B, and another is for system A. Okay, so you have there. So let us say this is your system B, and you have here system A. It depends on you. You can have system 1, system 2. It depends on you. Okay, just make sure that in the problem solving, the one that your solution will be not confusing. Okay, so you have here for block A. So if for block A, of course, you have to draw the free body diagram of that. And what are the forces found in block A or system A? So you have here the normal force. So this going upward, this is your normal force. Then of course the weight that is going downward, M sub A times G. And of course there's a tensional force going to this direction. Okay, so there's a tensional force going to that direction, represented T2. This is T2. Then you also have there the tensional force. Okay, so in this problem, the acceleration is going to positive x-axis. Okay, going to positive x-axis. So everything that goes against with the direction of acceleration should be negative. Okay, so you have here T2 going this direction, then the frictional force going to this direction, and so on. Then after that, we are going to apply now the forces, the summation of forces along x-axis and along y-axis. So notice that along y-axis, there is no acceleration, only along x-axis. So the second law becomes this one. So you have summation of forces along y is equal to 0. Then take into account all the forces along y. So we have the normal force going upward, you have there, and minus the weight, which is going downward, equate that one to 0. And then you have here the normal force, which is 147 Newton. Okay, so with that, the importance of this actually is again to compute for the magnitude of a frictional force, because the system is non-frictionless system. Okay, so along x, we have here the acceleration along x. So we've got to use the second law of Newton. Summation of forces along x, or the net force along x, is equal to m times a, m sub a times the acceleration. What are the forces? So you have here T1. The T1 goes with the direction of the acceleration. So this T1 should be taken to be positive. Okay, so positive. Then the T2 is going against the direction of the acceleration, then you have here minus T2, and so with the frictional force, that is equal to m times a. But if you're going to look into the system, so there's a lot of unknown. You have the acceleration, which is unknown yet, and you also have T. This is again, I think this is T2. The T2 is also unknown. So we've got to create another equations so that one of the variables or the unknown can be eliminated. Okay. So further, the equation is being expanded. So the frictional force becomes now mu times mg, m sub a times g. So this refers to this one. I mean, yeah, exactly. It refers to that one. Okay, so we just leave this one as our equation 1 because we cannot resolve this equation yet. Meaning to say that we have to find another equation. Okay, so if we're going to look at the problem again, the common between the variable is common, shared, mutual by this masses is T2, meaning to say that we can actually eliminate T2 because it is common between these two. So that's what we are going to do. Okay, so we are going to create another equation such that we will be able to get the link between system A and system B and to remove or eliminate T2 because that's the common of the two. Okay, so you have here the free body diagram for system B. So you have the normal force going upward and the weight going downward, and you have frictional force and of course the tensional force, which in this case for system B goes with the direction of the acceleration. Therefore this one will be taken to be positive. Okay, so the same with A, we are going to start along Y because along Y there is no acceleration. That is why you have here 0. Then normal force minus mb times g. Then normal force then is equivalent to 98 Newton. Then again it will be used in computing for the frictional force. Okay, so you have here summation of forces along X is equal to mb times A. So take into account all the forces. So you have here P2 going to the acceleration, goes with the acceleration direction. Okay, so you have here positive minus the F, which is against the acceleration, is equal to mb times A. Then you have here the expanded form, wherein we are trying now to plug in the weight as mb times g, and of course Newton, coefficient of friction, so that we'll be able to have this frictional force. Then next to this, we'll leave this one as our equation 2. Then notice that you have here the common, so you have T2, then in equation 1 you also have T2, so we can eliminate T2. In this case we can either use combination, or substitution, or by virtue of elimination. In this case I am using elimination, or I just add the two equations. So by adding, notice that T2 is positive, then for equation 2, then in T1 T2 is negative, so we could just eliminate them. So what will remain is T1 minus, you have mu ma times g, minus you have this one mu mb times g is equal to this one ma plus mb. Then you can factor out a. Okay, so with that, by doing further mathematics or rearrangement of the variables, we come up with this equation. Then plug in all the values for T1. You have already the force there, the mu, then you have the g, then you have the a, then plug in, and voila. Acceleration of the system is 1.208 meters per second squared. Okay, so going to positive x direction, that is why it's positive. Okay, if this one goes in the negative direction, negative x, then this one has to be negative. Okay, so that's it. So the third problem that we're going to have is problem wherein the system or the object is placed along or in an inclined plane. So it is placed in an inclined plane. Okay. So you have here an object, 10 kilogram mass. It is being pulled upward by a tensional force which is 20 Newton. Okay, so you have here the angle of inclination is 30. Then if I'm going to draw the forces, so you have here the weight. Actually, you have here the weight. This is m times g, and of course the normal force, which is always perpendicular to the how do you call this one, the surface or the floor or whatever it is. So this is our normal force. So the normal force is being exaggerated. Okay, so that's being exaggerated. Okay, so you have here the normal force that is going upward, okay, perpendicular to the surface. And notice that you have here the mu, the coefficient of kinetic friction. Therefore, there should be a frictional force acting on the system, and of course, it goes against the T2, which this one is assumed to be going in the direction of the A. So you have here the frictional force. Then you have here the T2. Okay, so in this problem, actually, what you should do is to rotate the Cartesian coordinate system. Unlike with the previous examples that we have, the Cartesian coordinate system is, say, it looks like this one. Okay, that's like that. However, in this case, we're going to tilt the axis or the Cartesian coordinate system at angle 30. So this is a technique actually in your pre-calculus, that is rotation of axis, translation rotation. Okay, so you have here your new y, then you have here your x. So in this case, for us to utilize this one, the rotated system, then we have to, how do you call this one, to decompose this component, the weight. So we have to decompose this one. So this one should become, this is angle 30. Okay, so they have the same angle. So this is m g, that is sine 30, and this one here parallel to the surface of the inclined plane is mg cosine 30. Okay, so you have there. Then later on we are going to apply the okay, so apply the law of Newton, second law. Okay, so you have here the normal force, friction, then component. So notice that we don't have to use the mg anymore. Rather, we are going to use the mg sine 30 and of course the mg cosine 30, which basically the component of the weight. Okay, so proceed. Though we have here the free body diagram, we have there. You have here the new Cartesian coordinate system is being tilted or rotated at 30 degree angle. Okay, so we are going to apply the second law of Newton along y. Now, always bear in mind that you have here the A in this direction. If this is the direction of the A, then everything that follows A should be positive, and everything is against it should be negative. Okay, so along y we have summation force along y is equal to 0. So the forces along y, we have the normal force and of course the component of the weight, which is equal to, is this cosine? Really? Wait, let me check. Okay, so forgive me, this is wrong. What I have written in this, again, the error again wasn't checked. I should have been thorough in checking this one, although I was the one who made this. I think this is some typo. Okay, so this part here along y, so you have sine, because this one, I mean, no, I was correct. This should be changed. Okay, even I being mistaken. Okay, so this one here is adjacent. This is adjacent to angle 30. So my picture actually isn't good to look at. So this must be cosine 30, and this one is opposite to this angle. So this must be sine 30. Okay, so I'm sorry for that. So you have here mg cosine 30, then applying along y. So you have the normal force, then mg cosine 30 is equal to 0. Then the normal force then is mg cosine 30. Then we're going to use this one later to compute for the frictional force. Okay, so we may choose this one to be equation 1, or if you have lots of equation, you may have equation 1, 2, and 3, but in this case you can have 1, 2, and so on, or you may not name this one. Anyways, you have here this given, all of this one to be computed. Okay, so along x-axis we have summation of fx is equal to ma. Then the forces along x, we have the tensional force. This is the applied force actually using a rope, which is parallel to the surface. By the way, if the rope is not parallel to the surface, then you have to take the component again of the force applied using a rope. So it will be more complicated than this. Okay, so you have tensional force minus frictional force minus mg sine 30. Notice that the mg sine 30 goes in this direction. That is why it is negative. Again, it is against the friction, the acceleration of the system. Okay, so it's equal to m times a. Then rearrange, a little rearrangement of the, how do you call this one? Rearrangement of the equation such that a is on the left side and the rest will be on the right side. And plugging in all the values, you come up that acceleration of the system is equal to 6.56 Newton. Meter per second, I'm sorry. My God, the cat is wailing, looking for a partner. I'm sorry for that. Okay, so you have that the acceleration of the system. Now, we have here this another problem. This problem number 4. I really like these problems like this because, you know, it makes our brain cells being challenged. Okay, so you have here an object A and B. So A is resting on the inclined plane while B is hanging. Okay, so the inclination of the inclined plane, of course, is 30, and you have here the frictional force, which is coefficient of friction 0.04. Okay, so again, the problem in this system is to find the acceleration of the system. Okay, so in this kind of problems, you should actually assume the direction of the acceleration. You are going to assume. You can actually assume the direction of the acceleration to be in this direction. So if this one would accelerate in this direction, then this one would follow. It will go up. Okay? So the same through with what we had earlier, that everything that goes with the direction of the acceleration should be taken to be positive, and against the direction of the acceleration should be taken to be negative. However, in this case, I'm going to assume that the direction of the acceleration going upwards in the incline and going downwards for the hanging object. Okay, so I think that is being used in this problem, so I forgot. Okay, so you have here. Then the next thing is you're going to decompose, to put the system, superimpose that one in the Cartesian coordinate system. So that is a free body diagram. So you have here the free body diagram for your system A. Okay, so you have there So normal force, the frictional force. Okay, so the acceleration is assumed to be in this direction. Okay, so you have there. So you have n. For along y, you have n dash 1 minus mg ma cosine 30. So you have here the normal force then is this equation 1, which will be used later on whenever the frictional force is being determined, to determine the frictional force. And along x, so you have t minus frictional force minus mg sine 30 equals to ma times a. Okay, so if you're going to look at the figure in here, okay, this is t, you have here another t. Okay, so the two systems are actually connected. It has common variables, and that is the tensional force. Okay, so notice that also in the equation 2, I mean, you have two unknowns. You have the tensional force and the acceleration. Okay, so we are going to create another equation so that okay, so you have here, in this case, we should find an equation such that it will create such that this one will be eliminated, because that is common for two systems. So free body diagram of the system for system B. So you have here the tensional force going upward and then the weight which is going downward. Okay, so it's very easy. You don't have actually to compute for the normal force for system B, because it is not resting on the floor. It is not being pushed on the wall, so there is no interaction on the wall, unless if you're going to have this one in the wall, then push that one. You may compute, say for example, I have here a wall, then I'm going to have this object here, then I'm going to push say F1, of course, then the surface here, the surface will of course create another force, and that is basically the normal force. So it is not interacting along the wall on the wall, so it is basically hanging, so there's no problem. So in this system also, we don't have to compute along x, because the motion of course is purely along y. So you have here the acceleration of the block. Okay, so if you're going to look at the direction of forces, so you have mbg goes with the direction of a, so that is taken to be positive. Okay, so you might be asking, why is it that it's positive where in fact it's going downward? Well, it should follow on the whenever it follows the direction of the acceleration, then that should be taken to be positive. Okay, so that's your basis. Okay, then t is against the direction of the acceleration, then you have your minus, then you have this equation 3. Then we may now combine equations. So same through with 3, you have t as the unknown, and you have here also another unknown. So we have two equations, we have two unknowns, then we may eliminate one of the unknown. Okay, so we may now combine equation 2 and 3. So with that, we can eliminate the tensional, the t variable. So what will remain here is this one, mb times g minus the frictional force minus this one is equal to ma plus b. You may factor out a. So you have here finally the equation, a very beautiful equation if you don't mind. Okay, so just do your algebraic method, factoring, and so on. Okay, so you have here, then you have here this simplified equation. Okay, we are going to plug in the values. So you have this one. So notice that A is positive, so you have 2.2803 meters per second squared. Since this one is positive, then the assumption of the direction of the acceleration is correct. Meaning to say that block A will accelerate in this direction. This is correct. And of course for block B, it will accelerate in this direction. That is then correct. So our assumption is that of the direction of acceleration is correct. Now, when can we say that our assumption is wrong? Okay, so if you find this one to be negative, say if this one is negative, then it implies that the direction of the acceleration being assumed is wrong. So all you have to do is just to reverse, meaning to say that if this one is negative, the acceleration is supposed to be downwards from the inclined plane, and of course the hanging object will go upward. If and only if this one is negative. However, it is positive, then the acceleration, assumed acceleration is correct. Okay, so we have another problem. Problem number 5. Again, we have A and B with masses. Okay, with their masses. And this one basically is a double inclined plane. Okay, so the inclined planes have different angle of inclination. So it is given in this figure. So again, this is very nice. You will come up with a very beautiful equation for this. Okay, so you have here, just like with the previous example that we have, again, that is problem number 4, I guess, you're going to do the same with each blocks. Okay, so you have your tensional force, let us have this one as T, you have the normal force, and then you have here the weight going downward, that is ma times g, and of course the friction. Well, in this case, we have to assume the direction of acceleration. You might be confused. Which will be the acceleration? What will be the direction of the acceleration? Well, all you have to do actually is to assume first, because later on you will find exactly where will be the acceleration of the system. I think in this case, the assumption of the acceleration is going upwards for A. Okay, so it's going upwards for A. So the direction of acceleration assumed in this problem is in this direction. So you have here, if this one goes upward, meaning to say this one goes downward. Okay, so the frictional force, so this is somewhere here, this is F, tensional force, and this one, you have a tensional force, T. Notice that they are connected. Okay, then you have here the weight that is going downwards. This is mb times g. And then what else? You have here the normal force, and then what else? The components, of course. You have here the components. Okay, you have that one there. Anyways, it will be found. So you have here the component of mbg. This is cosine adjacent, so this is cosine 45. Then this one, this part here, this is mbg sine 45. This is 45. Okay, so this again is 40, 45. Okay, so you have some. So in here we may decompose this one, the components. This is component, so you have there, this one is m a g, again that is cosine 30, while this part here, this m a g sine 30. Okay, so you have there. So just make sure that you have taken into account all the forces. By the way, the pulley in this problem is said to be frictionless. Okay, so we neglect the friction and of course the masses of the cords. Okay, so let's proceed. So for system A, so you have here, just like with what I did, and again the acceleration goes in this direction, so that is why we have here the T to be positive, F to be negative. Okay, so along Y, normal force minus the MAG cosine 30, so this one, then you have the normal force. Then for along X, so you have here T minus, this is positive, this is taken to be positive because it goes with the direction of the acceleration, minus F minus mg sine 30. Okay, so you have there. By the way, I forgot in this problem, I forgot to indicate the what I forgot. I forgot to indicate here the frictional direction. So the friction, let me have this one in blue color. So the friction goes in this direction. Control G, Z. Then I'm going to put the friction in here. So this is your frictional force. And of course, I'm going to say to move this one. Okay, so to move that one there, going to that direction. So voila, yeah, there. So that is the frictional force. Okay, so I just forgot. Okay, so we are going to have the color to be red. This is the usual. Okay, so you have here along Y, so you have this equation now that is used to compute for the normal force to be used in frictional force. Okay, so you have there T minus F minus MA sine G sine 30 is equal to MA. So notice again that this one and this one are unknown, so you cannot solve that one. One equation, two unknowns, we cannot solve that one. Okay, so further we have this, and then we have this equation 2. So we cannot do anything with this yet because you have here again the unknowns. Okay, so we are going to proceed to system B. Okay, so the same process. The acceleration goes in this direction, so your tensional force becomes negative. The frictional force becomes negative also. It's always negative. Anyways, okay, so it depends on the situation. And of course, the free body diagram matters on this. Then normal force, then you have here the components of the weight. Then proceed to the equation of the equation. So you have here N minus MB, this is along Y, and you have here equation number 3. Okay, then along X, so you have MB sine 45 minus F minus T. Okay, is equal to MA MB times A. So again, this is unknown. So you have here unknown, then this is for equation 4. Now we are going to combine equation 2 and equation 4 in this case. So we may now be able to remove, I just add the equations. So you have here this one. The variable now T is being removed. So what remains here is A, and we can compute for the acceleration right now because the remaining unknown is only A. We have just eliminated T. This is common for the system. Then further do further mathematical operation such as simplifying the equation. Then you have here this one. So we just factor out, or I just factored out the B in this case. Okay, so I know this is the resulting equation after we add this one. So it will be added actually. So let me do this one for you guys. So you have MB g sine 45, then this one minus mu mbg cosine 45, then this one here minus mu mag cosine 30 minus mag sine 30 is equal to this one. You have here m sub a plus m sub b times, of course, the acceleration. Okay, so you have here, then it is just being factored out, mb and ma being factored out. Then do further mathematical operations. So you have here acceleration is equal to this one, this expressions that we have. Then you have that one. Plug in all the values. Notice that this is mass, this is kilogram, this is dimensionless. You have kilogram, dimensionless. So kilogram numerator, kilogram denominator. Then it will cancel, equivalent to 1. Then the acceleration, which is 9.8 meters per second squared. Now, so you have here acceleration is equal to 5.3450 meters per second squared. Then the assumed direction, so the assumed A is correct. Okay, so because this one is positive. Okay, so if you're going to look back on the system, okay, though this one is 6 kilograms, you might think that it's lighter compared to A, so the acceleration should be going to A, but we must take into account also the angle. Okay, the angle plays a role in the direction of acceleration. Okay, as the angle becomes bigger for B, though it is only 6 kilograms, the drag of the force, the net, will be in this direction still. Okay, if this one is 10 kilograms also, then it will accelerate the same this direction. If this one, maybe say this is 15 or 20, we don't know. If this one is much more higher than this, okay, much more higher, then this acceleration will have to be in this direction. And if that's the case, we will be able to get a negative value for our acceleration in this problem. But take note that we come up with a positive acceleration, then it is conclusive that the assumed direction of acceleration is correct. So that is all for this session. So looking forward that you learn something out from the things that being talked or discussed in this session. So wait for another maybe another concepts that will be present, another videos to be given, to be uploaded in my channel. Okay, so that's all for this session.